So in the first part of this section, we looked at the subatomic particles that made up an atom, the protons, the neutrons, and the electrons. And we defined a couple of terms. We said that the atomic number was the number of protons in the atom. We also defined the mass number as the sum of the protons plus the neutrons. And that made a certain sense. Although the mass number is an integer that I get by adding up the number of particles, protons and neutrons, because the mass of each proton and neutron is about 1 atomic mass unit, we can estimate the mass of an atom with its mass number. However, let's keep that clear. The mass number is an integer that I get from adding up particles. The atomic mass is the actual mass of the atom. Now let's look at one particular atom. The way they decided how big an atomic mass unit was setting by definition that a carbon-12 atom has an atomic mass of exactly 12 atomic mass units. That makes a certain sense to me that because carbon is atomic number 6, and mass number 12, that it's got 6 protons, 6 neutrons, the mass would be about 12 mass units. Well, actually for carbon-12, they set it at exactly 12, and the masses of the other atoms are determined relative to it. How they do that is going to be the focus of our first lab this year, and more about that soon. You'll notice also that in this definition, it talks about a carbon-12 atom, but there's more than one isotope of carbon. Most of it's carbon-12, but there's a little bit of carbon-13. So when we go to look at the masses of the atoms in the periodic table, we will see that we have to reflect the masses of all the different isotopes. The masses in the periodic table are weighted average of all the isotopes. So I've got a copy of the periodic table here. This doesn't come in your pre-lecture notes. I stuck it in, but you'll be able to find a periodic table somewhere. I just wanted to point out that this number here is the atomic mass. And you'll notice that it is not an integer. It is 12.01 atomic mass units for the element carbon. Carbon-12 was exactly 12, but when we weigh in the contribution from the small amount of carbon-13, that makes the weighted average atomic mass a little bit higher than 12. Here is a table from your textbook that shows the abundances of different isotopes of different elements and how they contribute to the overall atomic mass. So I'm going to look at boron, and in the periodic table, the atomic mass of boron is 10.81 atomic mass units. This table shows that there are 2 main isotopes, boron-10 and boron-11. And the masses of those would be, of each one, boron-10 would have atomic mass of about 10, and boron-11 would have a mass of about 11 atomic mass units. The true weighted average is closer to 11 than to 10. It's 10.81 atomic mass units. So that suggests to me that there must be more boron-11 than boron-12. And we can see that in the percent abundances in this column. The naturally occurring boron is about 20% boron-10 and about 80% boron-11. So it makes sense to me that the weighted average is much closer to 11 than to 10. A little detail while we're at it. The boron-10 doesn't have a mass of exactly 10, but it's darn near it. A proton and a neutron don't have a mass of exactly 1 atomic mass unit. So the masses aren't dead on 10 atomic mass units for boron-10, but it's pretty darn close. So suppose I wanted to calculate this relative atomic mass like I would find in the periodic table, just given the data in this table. Our next problem is going to show an example like that. The question is, what is the relative atomic mass of neon? Now, the word relative is sometimes left out. It's assumed that's what we mean. The atomic mass of neon would be a weighted averages of the mass of all the different isotopes of neon. So let's go back to the data. We'd have to have the data on the previous slide to be able to solve this problem. Down at the very bottom, I can see that there are 3 isotopes of neon. It's mostly neon 20, about 90% neon 20. But there's a little bit neon 21 and a little bit of neon 22. So I think if I weighed this all in together, the average atomic mass should be a little bit greater than the 20 for neon 20. Always good to have an explanation or an expectation that we can check the sense of our answer against. Now, how am I going to do that? I'm going to find the relative atomic mass probably I'll never say relative again, by adding up contributions from all the isotopes. On the previous slide, it said we had about 90% of neon 20. Now, I've got to determine a percentage of something, I've got to express that percentage as a decimal. 90.48, that's 90.48% as a decimal. And that's the weighting we're going to give to the mass of neon 20, or more precisely from the data, 19.9924 atomic mass units. And I'm going to add another contribution from the next isotope, neon 21. It has a very low contribution, 0.0021. That's 0.21% as a decimal. No, that's 7, not a 1. And the mass of that isotope is 20.9938 atomic mass units. Yeah, neon 21, mass is about 21 atomic mass units. Now you're ahead of me. We've got 3 isotopes, so here's the third contribution. It's 9.25% neon 22. The mass of neon 22 is 99.14 atomic mass units. So what I've got here are contributions from each of the isotopes, and I weigh in more heavily the most abundant isotope. Now, you've got all the data. I see all your numbers. If you just want to jump to the answer, that's fine, but I'm going to do it in steps because significant figures are always at the back of our minds. This is the kind of problem where you're going to get in a snag because it's got 2 kinds of operations in the same question. So first I'm going to do a multiplication, 0.9048 times 19.9924. And I'm going to store that in memory 1 with no round off error. But that is, to the correct number of significant figures, 18.09 atomic mass units. I've got 4 significant figures times 6 significant figures, so there's 4 significant figures in the result of that first multiplication. Now for the second one, 0.0027 times 20.9938. And I'm going to store that in memory 2 and report the 2 significant figures that I'm allowed. 0.057 atomic mass units. Last term, 0.0925 times 21.9914. And I'm going to store that in memory 3, but I'm allowed 3 significant figures, 2.03 atomic mass units. Okay, when I was multiplying, I worried about the total number of significant figures. Now I'm adding. And what matters while I'm adding is where the number ends. The first one ends in the hundredths place, the second one ends in the thousandths place, and the third number ends in the hundredths place. And I'm limited to the least precise value. In other words, I'm limited to the nearest hundredth place. So, despite the fact that my calculator shows many more digits, I'm going to report it to the nearest hundredths place, and of course, always with the units. And I think I got a little problem there. That doesn't match what I've got in my notes. Let's add that up again. 18.09 plus 0.057 plus 2.03 equals 20.18. How did I know I'd made a mistake? Well, not every question can you tell, but this kind of problem is to calculate a relative atomic mass, and that's what we find in the periodic table. So when I just took a quick glance at the periodic table, my first value was close, but it didn't match. I didn't make a mistake on purpose, but since I did, let me tell you, you've got to go back and double check your work when you have reason to think you've made a mistake. Okay, the important point is, now that I've double checked it, it does add up to the relative atomic mass in the periodic table. To finish this section, let's look at the first experiment we're going to do in the lab, as I promised you. In the lab, we're going to determine relative atomic masses as well, but we're going to have a very different kind of data than we did in the last question. So let me talk you through the approach we're going to use in the lab. You're going to actually make a compound in the lab by combining two elements. In the lab, you're going to combine magnesium metal with oxygen gas. But so that I don't steal all your fun, my example here, which is exactly the same example that's in the introduction in your lab manual, we're going to combine calcium and oxygen. And in this particular case, I have to tell you authoritatively, because we don't know how to do this yet, allegedly, that the calcium and oxygen are in a 1-to-1 ratio. Okay, so these are in a 1-to-1 ratio, and what I'm going to do to solve this problem is set up a ratio. I'm going to consider the compound calcium oxide on a molecular scale, where we've got calcium and oxygens sitting near each other. But I'm also going to look at them on a macroscopic scale when I get a big pile of calcium oxide as a result of the reaction. In the lab, you're going to make magnesium oxide. You'll see a white powder, and that's on the macroscopic scale. So I'm going to set up a proportion here. What I'm going to show on both sides is the mass of all of the calcium in the compound to the mass of all the oxygen in the compound. And on a microscopic scale, that would be the mass of one calcium atom to the mass of one oxygen atom, because in the compound on a microscopic level, there's 1-to-1. Now on a macroscopic scale, we need the mass of all the calcium in this real-world sample. We can do it in this experiment, but not for every reaction. This is a special kind of reaction where all of the mass of the starting materials ends up in a single product. What I care about is the mass of calcium in the compound. But because of the law of conservation of mass, the mass of calcium in the compound is the same as the mass of calcium that reacted. In other words, 5 grams. Similarly, because all of the oxygen in the compound came from the oxygen gas, I can say that 2.0 grams of oxygen ended up in the compound calcium oxide. So here we are, just to summarize again. On the particulate scale, there's the ratio of the masses of calcium to oxygen. And here on a macroscopic scale, that's the masses in the compound. All right, now we're ready to go. I want the atomic mass of calcium, and by definition, atomic mass means mass of one atom. So I'm going to rearrange this to solve for the mass of one calcium atom. Whoops. That would be 5.0 grams over 2.0 grams times the mass of one oxygen atom. In the introduction to your experiment, it's given that the mass of an oxygen atom is 15.9994 atomic mass units. So now we work our units here, and we find out that the mass of a calcium atom turns out to be 5 divided by 2 times 15.9994. And to the two significant figures I'm allowed, that's 40 decimal point atomic mass units. If you check out the periodic table, that's going to be a pretty good value for calcium. If you don't get it exactly right in the lab, of course, there is experimental error, and that doesn't worry me a bit. It would kind of worry me if you got exactly the right value. This example points out why the word relative was part of the name, although I'll probably never use it again. We found the mass of calcium relative to the mass of oxygen. And really, in the periodic table, all of those masses are relative to the mass of carbon, which is set by definition at 12 atomic mass units. All right, I'll sign off for this video, and we'll talk about chemical formulas next.